speaker is going to present about pruning and optimizing large language models in an era of GPU scarcity. Our speaker for this topic is Ashar Islam, and he's from College of Science and Engineering, Hamad bin Khalifa University, Doha, Qatar.
Thank you very much. Hello everyone. As the chair said, my name is Ashar Islam. I work in a university in Doha, Qatar, a small tiny country if you've heard of it, which recently hosted the FIFA World Cup. So my talk today is about pruning and optimizing large language models in an era of GPU scarcity, and this basically comes under the umbrella of sustainable AI. So as you have seen the way the models are expanding these days, every day you hear a larger model has come, 4 billion, 8 billion, it's just a numbers game nowadays. But then I would like to stop and think for a while. So when you see a car, right, you see the exhaust pipe, you see the smoke coming out of it. But when you write code, do you ever think what is happening at the back end? What is the carbon emission that is happening? Just because you can't see it doesn't mean that it's not happening. Somewhere in the world, there's a GPU which is being cooled by a lot of water, which is utilizing a lot of electricity, and which is causing a lot of carbon emission. We don't see it, but it actually happens. Let me just give you some numbers to push my story. So this is the BERT model, which is one of the earlier NLP models by Google, which had around 110 million parameters. Now to train it on GPU, the carbon emission is equivalent to a round trip across the US. And then for ChatGPT, the earlier models, which had 137 billion parameters, training that on GPU is equivalent. The carbon emission is equivalent to the carbon footprint of 13,000 Americans annually. Also, it's not just about the training. When you deploy the model and people start using it, then if you see here, because ChatGPT has a huge number of users, one of the largest in the history of time. So that has a carbon footprint. The usage has of around 93 people in US. And the monthly electricity consumption of ChatGPT is equivalent to 90,000 people in Denmark. Also the matter of water. Training the ChatGPT, which required around 700,000 liters of fresh water, you could use that water to build 320 Tesla vehicles or BMW cars. And for each conversation that you have with ChatGPT, around 20 to 50 questions and answers, it gulps around 500 milliliters of water. So, the amount of data in the world is finite, but we can say that as compute increases, people are ambitious, that we are only going to come up with bigger and larger models. Which brings us to the question, is there a way we can change this a little bit, we can pull the reins a little bit by proving that you don't really need you can remove the fluff out and have a sleeker version, faster and lighter version of the models. So this is what we are going to talk about today. Now, there are many ways of doing this, of optimizing large models or optimizing large neural networks. You might have heard of something called quantization, where they say that, okay, the models are floating point numbers which take around, say, 20 bits for each parameter. What we can do is we can reduce the number of bits that represent each number. That's one way of going. Another way is called pruning, which I'm going to discuss today. Before I talk about it, I need you to imagine with me what models look like. Mathematically, models are nothing but matrices. You have one matrix followed by another. The layers are basically matrices. Your input is a vector which gets multiplied with that matrix. The result gets multiplied with the subsequent matrix, goes on and on until the result. So this is what it is. Now think about it. If they are matrices, and if we could really convert a lot of numbers into zeros, so we could make them sparse, as they say. And that is the basic idea of sparsifying or pruning large models or large language models. So here I need to tell you about two types of pruning that happen. One is called the unstructured pruning. What you see in the middle is the neural network. So what you can do is you can pick and choose which weights you want to remove, or you can simply remove layers or remove neurons as a whole. Now what's the difference? In the first case, you have a granular view or a granular method of removal of weights which reduces the loss of accuracy. Whereas on the other hand, the problem is you're making them zeros, right? You're not really removing them from the system. So the matrix is still there, it is still occupying space, it is still getting multiplied. So it's a theoretical speed up or a theoretical advantage. Whereas in case of structured pruning, where you remove the layers or remove the neurons as a whole, you actually get some speed up and you change the architecture of the model as well. So another thing that we have to understand is the pruning criteria. Let's go back to the matrices. When you take all the parameters of the matrix and you make a histogram of it, like you put what say the values in the matrix were from -1 to +1. When you make a histogram, you'll probably see very less values at -1 and +1, and large number of values accumulating near the zero, the middle. So what we can do is we can choose a threshold. Let's say 0.01. So all the values which are between minus 0.01 and plus 0.01, we change them to 0 and we keep the bigger one. So that's the normal method of pruning. But when do you do that? You do that at the end of the training. Once you've trained your model, then you look at the weights. And this is where our contribution comes in, where we talk about evolution of weights. So here what we do is we don't just look at the model at the end of training. We take a magnifying glass and we look at the model at each epoch or each iteration of training. So that shows us a lot of interesting things. We see how the weights have changed across time, across the training epochs, from the beginning to the end. And we can see some discrepancies. For example, if you see here, from left to right, you have all the epochs, and vertically you have the weights, right? So at epoch n, which is the last epoch, you can see a weight with the value 9. So you would think it's an important weight. But when you consider its flow, its evolution across time, so we do basically a weighted average. It's simply multiplying the epoch number and divide by the total number of epochs. We can see that its importance is actually less. So there might be some weights which look important at the end, but maybe they were not so important overall. Maybe they just shot up at the last epochs for some reason. Because after all, neural networks are black boxes, so you can't always understand what's happening. So this is what it looks like. You have on the left-hand side, we have the original model. At every epoch, the weights change. We store that, we keep aggregating it on the bottom, and we have an aggregated importance at the end, and the final weights of the model at the end. What we now do is, we create a mask. So here is where we create the threshold. We say that, okay, of the importance matrix that we created, any importance which is between, say, minus 0.1 to plus 0.1, we want to make them zeros. So how do they do it? I want to show you the exact operation. So on the right hand side is a mask which has zeros and ones for the weights which I want to make 0. And what I do is I multiply the original model's weights with that mask. So obviously what happens is you get lots of zeros in the model now. But the ones you wanted to preserve, they're preserved because you just multiplied by 1. Now the moment you multiply with 0 and make lots of zeros, your model might lose some accuracy. So what we do is we perform retraining. So we keep on retraining, and as you know, when you do backpropagation, all the weights are changed by default. That's the framework, how PyTorch or Keras, anything works. So the model's weights keep on changing. So what we do is we consistently multiply the mask by the mask every time to ensure that the compression is restored. And this is another view, a more global view of what's happening. So we take one layer, we apply whatever I just told you right now, and we keep on applying until the last but one layer. So this is the forward propagation. This gives us theoretical compression because, like I said, it just chooses some weights and makes them 0. Then what we do is we again create some threshold. Let's say if 80% of all the weights of my neuron are 0, or 90%, let's just cut them off out of the system. So you see, in this way, we can actually cut off or just prune some neurons entirely from the system. So this is how the whole thing works. And this has the advantage of both structured pruning and unstructured pruning. So yeah, so this gives a summarized view. We have the weight evolution where we see how the weights change across time. We do forward propagation where we just apply a mask repeatedly to reduce the weights and retrain them. And finally, we do structured pruning where we take the worst performing neurons and just remove them from the system. So what are the benefits of this? We reduce the model size, we reduce the number of floating point operations. We've seen that the models become more robust because they reduce overfitting as well. It's easier to do transfer learning, I'll show you how, and you get a new architecture. So out of these, I'll show you 3 examples that we have done. So before going to LLMs, let me show you just how it did on convolution neural networks, because initially we worked with CNNs. So what we did was we took a couple of large neural networks, CNNs, on these 2 datasets, ImageNet and CIFAR10, and we tried to see how it would perform. So the green line is the unpruned accuracy, which is obviously flat. And as you increase your compression on the x-axis, we see how the accuracy goes. So we see that the orange line, which is our method, versus the blue line, which is the standard structured pruning, we see that our method sustains the accuracy longer before really dropping off. And this happens for the different experiments that we have run through. Now this was all about convolution neural networks. Let's see how it performs against noise. So you might have heard something called adversarial attacks. So we took this dataset of ants versus bees, and what we did was, that's an actual image of an ant. We applied some noise to it in such a way that the image doesn't change. To a human being, it still looks like an ant, but the model starts to classify it as a bee. So we took 20 ant images and 20 bee images, and we performed this perturbation. And then we tried to see how well a compressed model would work on this kind of a data versus the uncompressed model. So at the bottom, you have the uncompressed model, which had around 82% accuracy, versus at 39% compression, we saw that we had a little more higher accuracy. Why is this happening? Because we believe this reduces the overfitting of the neural network when you reduce the number of parameters. Also, another interesting thing was data transfer learning. So, for example, what we did here was we took the LeNet5 neural network and the MNIST dataset, and we trained a model on that. Now, what we are saying is there a way if we can reduce the number of data or the amount of data and make the model smaller, can we still attain a good accuracy? So what we tried to see is on the top right, you have 100% data with 0% compression, and these are the other cases, all the possible cases that you can have. So we saw that for fashion MNIST, we had to use 100% data. We couldn't reduce the number of data, but with a reduced model size, we still had higher accuracy. This is because the fashion MNIST dataset is a little more complicated than the normal MNIST dataset. But for the other datasets like HASI V2 and Kannada MNIST dataset, we saw that we were able to achieve a higher accuracy both with reduced data and a smaller model size. Which brings us to large language models. So the first experiment that we did on the large language model was we tried to write from scratch a ChatGPT kind of a model, a smaller GPT model with around 10 million parameters. We gave it training data was all of Shakespeare's work, and we tried to see how well it could predict the next token. And if you see the metric here was perplexity loss, which is the probability of predicting the next word correctly. So the lower is better. And here at 0% compression, we have a loss of 1.9. But as we increased the compression, we saw that to a certain extent, our model was performing better. Then afterwards, its performance went bad. So at around 60% compression, we were able to sustain the accuracy, preserve the accuracy that the original model had, even better than that. But in the review, our reviewers for this conference said, hey, not just one model, come on, do another model. So in the further works we took a really challenging example. So this is a Phi3 vision model. So what's this? This is not an LLM. This is an LMM, which is large multimodal model where you can give input and image as well as text, and you get a text as output. So for example, you give the model this image and say what is the image about, and it gives you the answer. You can even give an image with some numbers. So you see there's 1, 2, 3, and on the cactus there's a white 4. So we ask the model what is the object number 4, and it correctly identifies that it's a flower, it's a cactus. So what we did now is, so this model is a pre-trained model, it's 4.2 billion parameters. What can we do with it? We don't have much resources. So what we try to do, we try to think, hey, let's convert this model to a regressor model. Now, how's that possible? So we took a data set, which is called the Burberry products data set, which has images. And for each of these images, it has these properties. The most important one here is the full price. So it has images like these, and in the Excel sheet, it has the title, the category, and the price. So we said, let's train the model to predict the price. So because we can get text data out, let's just fine-tune the model in such a way that we tell that we expect you to give us only the product name, the category, and the full price. In this way, then we can use the full price then to match it with the original price and see how well the model works. So we're not going to talk about the language here, how well it performs, rather its ability to extract features from the image and give us the price of each of the objects inside the image. So this was the method. The pre-trained Phi3 vision, it's 4.2 billion parameter model, already trained. We fine-tune it for 10 epochs, and we save the mean absolute error that we get. And then we prune the model at different compressions and fine-tune and see how well it performs. So here you can see the different compression rates and the mean absolute error. The image shows it better. So till 30% compression, we were able to get a better mean absolute error. Lower is better. And then it really drops off like very bad. So this gave us the understanding that there is a possibility in this method. But what we realized was that our method works well for specialized use case. Now you might ask, so if I take this 30% compressed model and give it the questions I was giving before, like giving an object and explain the object, number of this, it won't be able to perform that well because we have fine-tuned the model. So preserving the generalizability of the model is still a challenge for us right now with compression. Also, if you remember the 10 million parameters model, we were able to compress 60%. But this one, we were able to compress to 30%. So that's our method has to still adapt to size. And another thing, important consideration here is, remember I was telling you we were storing the weights. Storing the importance of the weights. So it's like you need to have a copy of the model. For each parameter you have to store the importance of that weight. So if you have 4.2 billion parameters in your RAM, you're having to store another 4.2 billion parameters, which is not good. So which brings us to our future work. One important thing that we want to do is we want to really connect it to the amount of carbon emission that is saved, so that we can convince our stakeholders, that this works. And obviously, we need smarter pruning methods to so that we don't lose the generalizability and we don't have to save the entire structure, copy the entire model structure and save it. So yeah, this was what I wanted to present to you. One of the main motive of this talk was to just make you think that when you write a code, when you execute it in Google Colab or whatever, somewhere in the world some carbon emission is happening, and just to be mindful of that and maybe think about techniques to make this better. So thank you for listening and thank you for your time. Any questions if you have? Yes.
A little bit of a silly question, but I'm curious about your selection of Burberry.
Burberry?
What was the thought process?
So we wanted a data set which had images and some value along with it. One option could be take the images of faces and their age, for example. That could also create a regression model. But this one was huge. It had around 30,000 rows of data. So I thought, and it was varied. It's different kinds of images, not just you have gloves. So we thought this could really showcase the ability of the model well. Yes.
So when you say pruning a network, do you once you prune everything, do you give a new architecture or a new?
Yes. So we consider the new architecture and we fine tune the model again. So we do the training steps again, because the moment you prune, the model loses a lot of accuracy. Because see, the knowledge that was there in the small weights, we need to push them to the weights which are non-zero right now. So you have to do some retraining needs to be done. So that new architecture has to be trained.
Okay, the whole process now the initial training will take more time.
Yes, there's so 100 epochs there and then 10 epochs.
Okay.
Something like that. Yes.
So regarding training and when shall we prune that network? So have you identified certain kind of validation parameters or certain?
The most important parameter here is the threshold. So you have weights.
But is it the hit and trial that this threshold will be taken or?
No, yeah, that's a good question, which I had in my defense also. So thanks. So we need to see. Generally you will see a shoulder kind of a thing. At some point the model really falls, but it's very difficult to generalize it for all different models. So what we do initially is, we don't fine tune. We simply compress and check its accuracy. Compress, check its accuracy. Compress more, check accuracy. This automatically gives us some idea of where the shoulder is, and at that point, then we do the fine tuning. So we're not wasting much time retraining here. We're getting an idea of how much the model can really sustain on the compression you're doing, and when it really falls off, just before that we do the fine tuning. All right, thank you so much.